Good morning, sir.
Good morning.
Good morning, sir.
Good morning. So, are there any questions, doubts? Anybody, any question, doubt?
Sir,
Yeah.
sir, in stress relaxation, even in free, so when we say like epsilon xx is constant, and then in the letter that sigma xx is constant, so sir, is there any value above which only these conditions will happen? So
Any? Please repeat again. Be little louder.
any minimum like threshold value above which only this viscoplastic behavior will be there.
No, it is actually dependent on temperature. So, if the, as I had discussed, if the temperature, no, the operating temperature is close to glass transition temperature,
Okay.
then it
So only
behaves
the
as a viscoelastic material. So it will depict stress relaxation, creep, all those. If there is a constant stress, it would depict creep. If there is a constant strain, it would depict stress relaxation.
so it's not exactly depend on the value of that constant value which is applied.
No, it is not dependent on that. Of course, yeah, yeah, if the temperature is close to glass transition temperature, at any value of stress, it would show creep, and at any value of strain, it would show stress relaxation.
Thank you, sir.
Hello, sir.
Yeah,
Sir, you said that when temperature is less than the glass transition temperature,
yeah,
then it behaves like a solid.
yeah,
So by solid, like, do you mean like rigid solid or like
yeah. So now, yeah, we are saying that, yeah, it will not have the viscoelastic behavior. It can behave as a elastic material. Of course, at high temperature also you have hyperelastic behavior. So the strains are quite large within the elastic limit, and if it is T is less than Tg, then it is a solid. It would be more like elastic, and the of course the it will not be like hyperelastic where it can undergo large strains within the elastic limit.
okay? So will it be fully
Plasticity, of
linear
course,
elastic?
and then the depending on the stress level, of course, it can experience plasticity. If it is a solid, T is less than Tg. Even metals at high temperature, when the temperature is operating temperature is close to glass transition temperature, the metals also depict viscoelastic behavior like creep, stress relaxation, these phenomena.
Okay. So, sir, for temperature less than glass transition temperature, will
Yeah.
hyperelastic behavior be observed or no?
Pardon?
For temperature less than glass transition temperature,
Yeah.
will it depict some behavior like hyperelastic or it will not be there?
No, hyperelastic behavior may not be there at low temperature, less than the glass transition.
So it will be linear elastic or plastic, like
Yeah, it can be plastic also, linear elastic or plastic, but before plastic deformation or failure, the strains will not be large. So that's the main difference with the hyperelastic behavior. Hyperelastic behavior before the material fails or within the elastic limit, it can undergo large strains like 200%, 300% strain.
okay, sir.
But this will not be the case for T less than Tg.
Okay, sir.
So are there any other questions? So yeah, if there are no questions, let me start.
uh, if so are we doing the are we loading the material till plastic loading condition?
So here we
Can
are,
this
whatever range we are loading, we are within the yeah, elastic limit. So we are not talking about plasticity. Although there can be viscoplasticity. So where the material, the stress levels are higher, so that viscous effects are also there, and plastic deformation, permanent deformations are also there. So that situation can be there. Here, what we are considering here is a viscoelasticity. Yeah. So the
Oh,
stress limit, there would be limit on stress, obviously. No, if the stress is more than certain value, it can undergo viscoplastic deformation.
okay, sir.
Yeah.
Hello, sir.
Yeah.
Sir, like you showed by graph the stress, relaxation, and creep.
Hmm.
So suppose if we have a like three-dimensional body.
Yeah. Pardon.
Suppose like we have a three-dimensional body. So
Yeah.
for that, will we be plotting sigma equivalent?
Yeah, if there is a multi-axial loading, so you will have to look at the stress and the applied stress versus time and the strains in different normal strains and shear strains in different directions and planes. You'll have to look at all of those. Or if you apply a strain in a particular direction, then you'll have to look at all the components of stress separately.
Okay, so like in creep, we will keep all the components of stress constant.
Yeah.
Sir, one doubt regarding the plots you have given. So, sir, if we see the plots of like epsilon xx and sigma xx,
Yeah.
one of them is like constant and other one is like varying with time.
Yeah.
Uh, so, but sir, like we also have one equation, right? Sigma xx is like linearly dependent on epsilon xx. Is that not applicable here?
We are going to discuss the different models. So that I'm going to discuss today, the different constitutive models for uniaxial case. First I will discuss. So what are the
Oh,
stress strain relation for viscoelastic materials? What are the different models? I'm going to discuss that.
okay, sir. Basically, like we will have a completely different things for this particular
Yeah,
viscoelasticity.
we will have stress strain relations, but they are not elastic, no viscoelastic. So it will have some rate dependence. So the
Okay,
stress
sir.
and strain rate will come into picture in addition to stress and strain.
Okay, sir. Okay.
Yes. So then let me start. So today I'm going to discuss basically the viscoelastic constitutive models for uniaxial case. Is my screen visible? Hello, is my screen visible?
Yes, it's
Visible.
visible.
Okay. Viscoelastic constitutive models, and this we will do for uniaxial state of stress. And then of course we will generalize it to three-dimensional case. So the simplest models is what is known as the Calvin-Voigt model. So see, the material is there as it is. These are different models. So what are available, and we can use for the simulation. So first is this Calvin.
Sir, are these based on experiments?
Yeah, yeah, they have ultimately yes. You have to predict correctly the creep behavior with the stress relaxation behavior. So they, people have proposed different models and which model can predict what accurately. So yeah, they are ultimately the uh, final choice of the model is yes based on the experimental comparisons. So in this model, what is proposed is that you have to have basically the elastic part in it and viscous part in it. So elastic part here is represented as a linear spring, and viscous part of the behavior is represented by a dash part, linear dash part. So in this Calvin-Wag model, the spring, one is spring elastic element, basically elastic element and the viscous element, these two are taken in parallel. So it is assumed that no, the material behavior can be represented by these two. So there is a, I'm denoting the uniaxial state of stress as sigma and corresponding strain as epsilon. So sigma and epsilon is there. And see, this is elastic element, as I already said. And let us say the Young's modulus is E. E, yeah, Young's modulus. Young's modulus is E for that, and this is the viscous element. And let us say the viscosity of this element is eta. So eta is viscosity. So in this model, what you will see that both the models would experience basically the same strain. The elastic element as well as the viscous element will experience the same strain, but stresses would be different, and the total stress would be sum of the stresses in the elastic element and the viscous element. So we can say that elastic and viscous elements will experience same strain. Will experience same strain. So now if you look at the stress in the elastic element, so let me denote that by sigma E. So the stress in the elastic element would be Young's modulus times strain, and the stress in the viscous element sigma eta, this would be proportional to strain rate. So it would be, say, viscosity eta times epsilon dot. So now if you, so this is the elastic for the elastic part, and this is for the viscous part. Now if you look at the total stress sigma, so sigma will be equal to sum of the two. The total stress is going to be, because the both the elements are in parallel, will experience same strain, but the stresses would be different, and the total stress would be sum of stress in the elastic element and the viscous element. So sigma E plus sigma eta. So sigma E is, we have seen, either is E into epsilon, and the viscous element stress is eta into epsilon dot. So this is what you have, and if we divide this by Young's modulus of the elastic element, so we can say that sigma upon E would be epsilon plus eta upon E times epsilon dot, and this ratio eta upon E is known as the stress relaxation or retardation constant. So we can write this also, epsilon plus tau times epsilon dot, where tau is equal to eta upon E, and this is known as retardation or relaxation constant. So yeah, this is the, so you can say in this case the constitutive model is sigma is equal to E into epsilon plus eta times epsilon dot. So you would see the stress is a function of total strain and also the strain rate. So this is is Calvin-Voigt model, where the stress is a function of this strain and also the strain rate. So the two things are coming into picture here. Now we want to simulate the same thing, the stress relaxation and creep behavior. So let us see that. So let's look at the response of this model under constant stress. So we want to look at creep, whether it is able to represent creep correctly or not. So let us look at that. So the response under constant stress, and that constant stress is, let us say, sigma naught. So what we are saying basically that stress, total stress is sigma naught. So sigma naught E, from the constitutive relation we have epsilon plus tau into epsilon dot. So this is the relationship we have. And now we want to, so this is the stress is constant, we want to solve for the strain as a function of time. So in this, the initial condition would be is that epsilon is equal to 0 at t equal to 0. So initially say the strain is 0. So if you solve this, this is a first order differential equation, and this is the initial condition. Sigma naught is constant. It's applied constant stress, in the, basically throughout the time duration considered. This is constant. So this is a first order differential equation. The solution will consist of the complementary function and the particular integral, and then the constant you can evaluate using this initial condition. So if you solve this, you will see that the solution for epsilon will come out as epsilon t is equal to sigma naught upon e into 1 minus e to the power minus t upon tau. So this will be the solution of this equation.
Hello, sir.
Yeah, yeah.
Sir, viscous stress, as we read in undergraduate, it is shear stress, and the elastic stress that we are using it is normal stress. So can we add it directly?
No, both of them are normal stress here. No, we are not talking about shear stress. We are talking about the normal stress. In both cases, these are normal stresses. Normal stress in the elastic part is sigma E, and normal stress in the viscous part, we are talking about this sigma eta. So both of them are normal stresses. We are looking at here the behavior under uniaxial normal stress, not the shear. So it's not shear stress. Of course, you can also write the similar thing for shear. So if it is
Yeah, yeah.
subjective to shear stress and shear strain, you can have similar relationship that tau is equal to tau e plus tau eta. So this is for the normal stress.
Okay, sir.
So both are normal stresses. So this is a solution. So that means what if you look at the the stress here on the vertical axis and time in the horizontal axis. So stress is constant and the value is sigma naught. And if you look at this strain response, what we are getting, so the solution which we have got. So if you look at the epsilon and t over here, and you see that the strain at t equal to 0, strain is 0, and then it is increasing with time exponentially. So this is how the strain response is going to be. So you can see that the creep is represented correctly in this model. The Kelvin-Voigt model represents creep correctly. So the conclusion from this is that creep is represented correctly. Now, if we look at for the same model, if we look at the response under constant strain, that's the second thing. I mean, these are the two simple cases we can think of, although actual scenarios may be much more complex, so we'll have to look at that. But first, we are talking of the simple cases. So, the response under constant strain. So, let us say that strain is epsilon naught. So what we are saying is that in this case we have epsilon versus t, and that epsilon is constant, that is equal to epsilon naught. So this is the case we are considering. The governing equation is the same, that sigma upon e, the general governing equation for Kelvin-Voigt model is epsilon plus tau into epsilon dot. Now because we have the epsilon dot 0, the strain is constant, so this term is actually going to be 0. So you will get any strain is epsilon naught, so sigma is equal to e into epsilon naught. So if we subject this to a constant stress, if we subject this to a constant strain, then you will see that it will experience a constant stress of e into epsilon naught. So that means the stress is constant. Whereas what we want is that it should depict actually the stress relaxation. So you can see that the Calvin-Voigt model is not sufficient. It represents the creep correctly, but not the stress relaxation. So the conclusion is that stress relaxation is not represented correctly. So then one more model is known as the another model, Maxwell model. These are two
Sir,
simple models. Yeah,
sir, like in last class when you drew the curve for creep,
yeah,
so there was an offset for epsilon xx. Like it was not starting from zero, sir.
yeah. So here I have taken that if you have epsilon is equal to epsilon naught at t equal to 0, so accordingly you can get this solution. I have
Okay, sir.
taken
So
epsilon equal
initially
to
it's
0 at
zero.
t equal to 0.
Okay, sir.
Yeah, you can accordingly get the solution if epsilon naught is equal to some epsilon naught at t equal to 0. So yeah, so then other model is known as the Maxwell model. So in the Calvin-Voigt model, the elastic element and the viscous elements are in parallel, and in the Maxwell model they are considered in series. So these are the viscous and elastic elements either can be taken. Say the simplest things is either in parallel or in series. So if they are in parallel, that is known as the Calvin-Voigt model, and if they are in series, that is known as Maxwell model. So in Maxwell model, as I said, element and the viscous element, they are in basically series, and say the total stress is sigma and strain is epsilon. The elastic element Young's modulus is E, and the viscous element the viscosity is eta. And in this case you see both the elements would experience same stress, but the strain would be different. So the total strain would be sum of strain in the elastic element and the viscous element. So you can see here both the elements will experience same stress. So now if you look at the strain in the elastic element, stress is same, so that would be sigma upon E. And if you look at the strain rate, that is what would be related to stress in viscous element. So epsilon dot eta would be equal to sigma upon eta. So now if we look at the total strain rate, so this is for the elastic element and this is for the viscous element. In elastic element, the strain is sigma upon E. In the viscous element, the strain rate is sigma upon eta. So now if you look at the total strain rate, say epsilon dot. So epsilon dot, we can write that the strain rate in the elastic part plus strain rate in the viscous part. And the strain rate in the elastic part would be E is constant, so it would be sigma dot. So that would be sigma dot upon E, and in the viscous element it is already sigma upon eta. So this is epsilon dot for this model. Now what you can do is you can rewrite this. If you multiply both sides by E, so you can write this relationship as E into epsilon dot is equal to sigma dot, and plus this side we will have E upon eta, which is 1 upon tau, so you can write it as sigma upon tau. So where tau is eta upon E, the same definition which we took in the Calvin-Voigt model. Now if you look at the response, again we want to see whether it can model creep and stress relaxation correctly or not. So let's again look at the response under constant strain. So if you look at the response under constant strain, and let us say that strain is epsilon naught. So now the strain rate is 0 because strain is constant, so strain rate would be 0. So this will give you sigma dot plus sigma upon tau is equal to 0. This will be the now the equation, because strain is constant, so strain rate is 0. And the initial condition, let us assume, let us say that the initial condition is basically sigma is equal to sigma naught at t equal to 0. So let us say this is the initial condition. So now if you solve this differential equation under this initial condition, again it's a first order differential equation, and since the right side is 0, so it will have only the complementary solution and homogeneous or complementary solution, and the constant you can evaluate through this initial condition. So final solution would be sigma as a function of t would be equal to sigma naught into e to the power minus t upon tau. So at t equal to 0, sigma is sigma naught, and then it is going to decrease with time. So that means now if you look at the graph, what this is representing is we have epsilon, and this side we have time, and the strain is constant, so that is equal to epsilon naught. If we look at the corresponding stress, sigma and t, so you will see that this is represented a behavior like this. This is sigma naught. So you can say that in the Maxwell model, the stress relaxation is represented correctly. So the conclusion is that stress relaxation is represented correctly. Now let's look at the creep. So that is response under constant stress. And let us say that stress is sigma naught. So we will have, because stress is now constant, so sigma dot is actually going to be 0. And the sigma dot is going to be 0, and sigma equal to sigma naught throughout the time instant. So now if you look at this equation, this equation, so we have sigma dot is equal to 0, so E into epsilon dot is equal to sigma upon tau from this equation. So if you solve for epsilon, basically you will get that as a linear function of time. So the solution will be, so the solution for the problem would be that epsilon t will come out as sigma naught upon eta into t. So we are of course assuming that epsilon is 0 at t equal to 0. That's the initial condition. So the solution of this differential equation is going to be this. So what you see here, that with the constant stress, the strain is increasing with time, but it is linear. Whereas what is observed experimentally, that it is also exponential. So it is representing a linear creep response. So it is neither the Kelvin-Voigt model nor the Maxwell model are capable of actually representing both stress relaxation as well as creep correctly. So we need a different model. So one of the popular model is known as the standard model. So a standard model means we take the element in parallel and also in series involving viscous and elastic elements. So in the standard model, or it is also known as 3-element model. So you have in this model, what is proposed is that you have one elastic element, and then in this together with this elastic element you have and the other element which is having elastic part and viscous part in series, and then now you subject them to stress and strain. So this is sigma and epsilon, sigma and epsilon. So the one which is purely basically elastic element, so that Young's modulus is denoted as E infinity, because for this model, if you look at the effective Young's modulus at infinite time instance, it would be just equal to the Young's modulus of this part. So that is what and this is nothing but because these two are, the elastic and viscous elements are in parallel, so it is like a Maxwell model. I mean, part of it is a Maxwell model. So let us say the elastic element has Young's modulus as Em, and viscous element has viscosity as eta m. And the stress experienced by, now we will see that both the parallel branches will experience same strain but different stresses. So let us say the stress in this is sigma infinity, and the stress in this is, let us say, sigma m. And you can say that this is basically the one elastic element and one Maxwell element are in parallel. So this is Maxwell element. So now in this, so this is the model you have. And now if you look at the, let's say the differential equation, the relationship between stress and strain we want to look at. So no, for the Calvin Voigt we had seen the stress strain relation. For the Maxwell model we have seen the stress strain relation. Now let's look at the Maxwell model. So now if you look at the total stress, so it is going to be sum of stress in the this element. So sigma would be equal to sigma infinity, that is stress in this, plus stress in the Maxwell part, so that would be sigma m. And of course the stress, because both the elements, the elastic element and the Maxwell element, are going to experience the same strain, so we can say that sigma infinity would be E times epsilon infinity, the strain in the no, we not the sorry, stress in the this elastic element is going to be E infinity into epsilon. The strain is same in both the elements, so that is E infinity into epsilon, and plus we will have of course this sigma m. And for the Maxwell element, if you look at the strain rate, strain is going to be experienced by the elastic and Maxwell element is going to be same. Strain rate experienced by the elastic and Maxwell elements are going to be same. So now if you look at the epsilon dot strain rate, so that would be equal to sigma infinity dot, that is the stress rate in the elastic element divided by E infinity, that would be the strain rate in this, and this will be equal to strain rate in Maxwell element, and the strain rate in Maxwell element is going to be strain rate in the elastic part of the Maxwell element, so that is sigma m dot upon Em, and plus the strain rate in the viscous element of the Maxwell, viscous element part of the Maxwell element, so that would be sigma m upon eta m. So these are the equations you have. So one equation is that total stress is this, and another is the strain rate is related to these two, no, in this manner. For this, the elastic element, the mixed elastic element and the Maxwell element. Now again we want to study the response under constant strain and response under constant stress. So first let's look at the, now for the Maxwell element, let us see how it behaves. So response under constant strain. So that is, let us, yeah, yes please. Yeah, any question? I think your voice is not, you are not audible. Yeah, somebody wanted to ask a question. Your voice is, you are not audible, your voice is not clear. So in this case, if we are looking at the response under constant strain, so basically epsilon dot is 0. So what you can do is epsilon is equal to epsilon naught and epsilon dot is 0. So if epsilon dot is 0, so from this equation you can solve for sigma m, because it is again a first order differential equation in sigma m. So you can solve this equation for sigma m, and then the stress in the elastic part is already E infinity into epsilon naught, so you can get the total stress. So if you look at the total stress would be sigma is equal to E infinity times epsilon naught, that is this part, plus sigma m, and sigma m you are solving from this differential equation, where epsilon dot is 0 because epsilon is constant equal to epsilon naught. So the solution of this equation, let's say the initial stress in the Maxwell element is sigma m naught, so this would be sigma m naught into e to the power minus t upon tau. So this will be the solution. And if you look at the plot of this, so now if you see here, we have strain and this side we have time, and the strain is constant, that is equal to epsilon naught. So if you look at the stress here, sigma versus t, so initial stress is basically the sum of these two stresses. So that would be, it's at a higher level, and then it will decrease, and finally it would get a response like this. So if you look at this steady state response, so finally this stress is going to be E infinity into epsilon naught. That is going to be the steady state response. And but as you see, under constant strain, this model is representing stress relaxation. Stress is reducing. So you would see here that stress relaxation is represented correctly in the standard model. Now let's look at, for the same model, let us look at the response under constant stress. So these are the two basic things we are first looking at. Now they're trying to, for the different models, we are trying to see how they respond under how they predict the response under constant stress and strain. So response under constant stress, that is sigma naught, sigma equal to sigma naught, and sigma dot is 0. So now if you know you want to look at this relationship, so we have already seen that stress is constant, so that is sigma naught is going to be basically sigma infinity plus sigma m. So now if you want to kind of write the the sigma infinity, let us say, so sigma infinity you can write in terms of sigma naught minus sigma m. And then if you want to write the strain, so because we know that the elastic element and the Maxwell element are experiencing the same strain, so the strain I can also get by dividing this through E infinity. So if the whole equation, if I divide it by E infinity, I can write epsilon. So epsilon would be sigma naught upon E infinity minus sigma m upon E infinity, because we know that sigma infinity is E infinity into epsilon. So epsilon is sigma infinity upon E infinity, which is sigma naught upon E infinity minus sigma m upon E infinity. Now if we look at the strain rate, the differential form of this, so I can say that epsilon dot will be equal to, because sigma naught is constant, so minus sigma m dot upon E infinity, that is epsilon dot. And the expression for epsilon dot, so this is an alternative way of writing the strain rate from the elastic element of this standard model. So but we know this relationship, that epsilon dot is purely written in terms of the Maxwell element in the standard model, that is this equation. So you can see that this epsilon dot is also equal to the sigma m upon sigma m upon sigma the sigma m upon eta m plus sigma m dot upon em. So we can also write it like this. So this is two alternative ways of writing epsilon dot. This we have already seen, and this is an alternative way. So now if you combine these, so you can actually write this equation as sigma m upon basically tau m. So if you multiply the whole equation by em, so you can get it as sigma m upon tau m plus sigma m dot into 1 plus em upon e infinity. So I think this is straightforward, the relationship you can derive. So now from this relation to this, and then the strain rate, and the other alternative way, we have already written the strain rate for the this element over here. Now this relationship, one way of writing is this, another way of writing is the epsilon dot is this. So I'm basically considering this equation. So this equation can be, that equation can be written like this. Now if you look at the solution of this equation, so again, assuming that no, the in this case we can this is a first order differential equation in sigma m. So you can solve for sigma m, and once you have sigma m, then from this relationship you can get your strain. So if you do the solution, I am leaving the solution to you, that first solve this differential equation for sigma m, and then from this you get your epsilon. So that will give you epsilon t is equal to sigma naught upon E infinity, that is this term, and the second term is, and of course while solving this equation you assume that sigma m is equal to sigma m naught at t equal to 0. That would be your initial condition. So when you solve this equation, take sigma m is equal to sigma m naught at t equal to 0 and then solve it. So if you will get that as a sigma m naught upon E infinity into e to the power minus t upon you will get tau m in the this is the relaxation constant for the Maxwell element, plus you will have this ratio of Young's modulus of the Maxwell element and the Young's modulus of the elastic element in the Maxwell model. So this is the expression you get, and again see this will be representing the increasing strain with exponentially increasing strain with time. So the conclusion is that creep is also represented correctly. So creep is represented correctly. So now you would see that when we are looking at the standard model, which has one element, elastic element in parallel with another Maxwell element, then it is representing both stress relaxation as well as creep correctly. So this is why this model is very popular model. So no, it is and then of course there is a generalized form of this standard model with more number of Maxwell elements in parallel with elastic element, and based on that we derive what is known as Croney series. So I will be discussing that. So but yeah, most popular one is this standard model, and then extension of the standard model. Now let me revisit the now can be equivalent, can we talk of response is changing with time, so can we talk in terms of equivalent modulus as a function of time? So for that, let me again revisit the Maxwell model. In a way, in the standard model also you have Maxwell element. So if you look at the Maxwell model, so we have seen in the Maxwell model that response under constant strain is let us say so if you look at the Maxwell model, so we have seen this response in for the Maxwell model. This is sigma t is sigma naught e to the power minus t upon tau. So that is sigma naught minus e to into e to the power minus t upon tau for the Maxwell model. Now we want to kind of get an equivalent Young's modulus, which is a function of time. So we divide this by strain, and strain is constant. So we will get Young's modulus, which will be sigma t upon epsilon naught. So sigma t upon Et we are defining as sigma t upon epsilon, and it's actually epsilon naught, you can see, and that will be equal to sigma naught upon epsilon into e to the power minus t upon tau. So you can see that this Et is equal to and let us say no, this sigma naught upon epsilon is E naught, so it is E naught into the power minus t upon tau. this E is actually the no modulus of your basically the elastic element in the Maxwell model. So you can say that Et equivalently we can say that for the Maxwell model the Young's modulus is changing as a function of time, and that's E into e to the power minus t upon tau. So here E naught, what is E naught? So where E naught is modulus at t equal to 0. So the conclusion from this you can say that Maxwell element represents exponentially decreasing modulus of the material. So the this is one thing. Now so far what we have seen, of course, you can always, whether even standard model you can get an equivalent basically the Young's modulus. So for the Maxwell element, for the standard solid, you will see that the basically equivalent modulus. So if you this equation, if you divide it by epsilon naught, so sigma by epsilon naught would be Et equal to E infinity plus Em into e to the power minus t upon tau. So for this also you will have an equivalent modulus which is a function of time. No, you can represent through an equivalent modulus as a function of time. So now in both these cases, all the three cases rather, we have seen the response under constant stress and response under constant strain. But in real situation we might have the strain which is changing with time, and then we want to look at the stress which will also be function of time. So for that there is a famous integral given by Boltzmann, is known as Boltzmann integral. So let us I will briefly talk about how this is arrived at. So Boltzmann integral. So in this what we are interested, so let's see, start with a hypothetical situation that this vertical axis is strain and this axis is time t. So let us say at some time instant t1 there is a strain epsilon delta epsilon 1 is given. So this strain is delta epsilon 1, and for some time it is constant, then another incremental strain delta epsilon 2 is given. For some time it is constant, and then again another strain increment delta epsilon 3 is given, and then again it is constant. So like that you have, so let us say this is at time t1, this is at time t2, this strain increment is given at time t3, and then under this we want to look at the response at some time t, the stress at some time t. So if you, for this now, if you look at the, if we think of either the Maxwell model or even the standard model, so we see that under the because here for some time the strain is constant, so it is like no kind of thing we are looking at is the stress relaxation. So now if we plot the the stress for this, so this side the vertical axis is stress and the horizontal axis is time t. So initially, once you have this delta epsilon 1 is applied, so if you look at this, basically the standard model, so when there is a constant strain is applied, so we see that because of that constant strain, the stress, there is one constant part of the stress, and then there is a constant part of the stress at t equal to 0 would be sigma infinity plus sigma m naught, and then it would be decreasing with time. So there would be some constant stress, no increase in the stress, and then it would be decreasing in time. So you will have the response when the moment delta epsilon 1 is applied. So you have this stress, and this stress would be actually equal to E naught into delta epsilon 1. And then it would because for some time the strain is constant, so there would be stress relaxation, so it will go like this exponentially. Then another again another strain increment delta epsilon 2 is applied. So because the strain increment is applied at that instant, so for this the material will behave as if at the initial state at t equal to 0. So again this stress increment would be E naught into delta epsilon 2, and then it would actually decrease. Then now you apply another strain increment, so again this increase in the stress would be delta epsilon 3, and then it would exponentially decrease. And this is at time t1, this is at time t2, and this is at time t3. So this is how the response would be. If you look at this material, this is how it is going to actually respond. So now if I look at the stress increments corresponding to each strain increment, so whatever I have drawn the figure, same thing, let me write it in terms of equations. So stress increments corresponding to strain increments. So now first let us say this one is delta sigma 1. So delta sigma 1, I have written it as E naught. So that is Young's, E naught is the Young's modulus at t equal to 0. So since Young's modulus is a function of time, if we replace t minus t1, so at t1 equal to t equal to t1, E would be E naught. So you can write that as E E at t minus t1. So at just t1 equal to 0, you will have this as E naught, and subsequently of course the modulus would be decreasing with time. So it would be the stress increment due to a delta epsilon 1, the stress increment due to this strain increment delta epsilon 1, that is this part of the curve. This part will be represented by this equation. Similarly, delta sigma 2 will be E at t minus t2, because the strain increment delta epsilon 2 is applied at t equal to t2. So for that part of the strain, it would behave like the Young's modulus at t equal to 0. So we are taking t minus t2. So at t equal to t2, E will be E naught, and the stress then would be delta epsilon 2. So that is actually representing this part. Now if you look at this part is represented by this equation. So similarly, you can write, you can have n number of increments. So E t minus t3 into delta epsilon 3. So like that, you can have n number of increments over here. So now you can, any number of increments you can have. So now if you look at the total stress at any time t, total stress sigma t would be equal to summation of all the incremental stresses, which are all functions of time. So that means you can write the sigma t is equal to summation I going from 1 to n if there are n strain increments. So then we will have E t minus ti into delta epsilon I. So you can write it like this, this relationship. Now let us say the strain is a continuous function of time. In this we are assuming that the strain is incremented discretely at discrete time instances. Now let us consider a case that we have the strain which is a continuous function of time. So we want to generalize this relation. If strain is applied as a continuous function of time, so then this summation would be replaced by integration, continuous function of time. So then what will happen is that sigma t in that case will be replaced by sigma t would be integration 0 to t. You are summing all the strain increments up to time t. So since it is a continuous signal, you write it as E t minus t dash into d epsilon. So the integration is now this in d epsilon you can write. So now see we are writing ti as t dash over here, and now the strain, since is a continuous function of time, this increment in strain is replaced by differential change, a differential increment. And now you can also rewrite this. So sigma t can be written as integration 0 to 2 t e t minus t dash. So this e t minus t dash, meaning e is evaluated at t minus t dash time instant, and this we can write it as d epsilon by dt dash into dt dash. So now this is the expression for the stress for a general strain. Now when the strain is changing as some function of time, so we can use this relationship to find out the basically your stress as a function of time. Stress is as a function of time. Here if you look at the E, so E as a function of time, if you look at the standard model, it would be E infinity plus Em e to the power minus t upon tau m, and we can increase the number of elements and actually increase the accuracy of the model. So now if you see earlier for the whether Calvin Voigt or Maxwell or standard model, we have represented the relationship between stress and strain in the form of a differential equation, and through the Maxwell this Boltzmann integral, we are able to write the relationship between stress and strain in the integral form. So this is the relationship between stress and strain is in integral form, whereas no earlier what we discussed is the stress strain relationship in differential form. So you can either use those differential forms of the constitutive relation, stress strain relation, or you can use this integral form. Most of the time, most popular one is this integral form of the stress strain relationship using this. Where now we use generalized modulus as a function of time, known as Prony series. So we have more number of elements in that. So I have already said that this comes from the standard model. So let me revisit that standard model. So how we get this Et as infinity plus Em. So if you look at the standard model, under constant strain, we have seen that sigma t is equal to sigma m naught e to the power minus t upon tau m, and plus you have the stress in uh, uh, the elastic element of the standard model, so E infinity into epsilon naught, and if you divide this by epsilon naught, so you get sigma t upon epsilon naught as Et. So this term will give you E infinity, and then this sigma m naught upon epsilon naught will give you Em. So that is I have already written Em e to the power minus t upon tau m. So this is how you get this from the basically what is known as the standard model. So then there is a concept called Prony series. See, this has got in this, if you take the standard model, so we are having an equivalent Young's modulus, which is a function of time given by this expression. So it may not, it would qualitatively, it will represent this standard model with this equivalent Young's modulus as a function of time will qualitatively will represent accurately the stress relaxation and creep, but quantitatively exactly it may not represent. So for more better quantitative representation of creep and stress relaxation, we use more number of maximal element in parallel with the elastic element, and based on that we get an expression for Young's modulus which is known as Prony series. So let me talk of this Prony series. So this is the basically generalization of the standard model. So as I said, you have one elastic element, and then you have multiple maximal elements in parallel. So you have like this, you can have n number of elements in parallel. This side you will have, we are still talking about uniaxial cases, so you will have sigma and epsilon. The Young's modulus of this elastic element is infinity. That is actually why this is denoted as infinity, because E at t equal to infinity will be just E infinity. The other contributions will go to 0. and let us say this is E1 and this is eta 1, this is E2 and eta 2, this is E3 and eta 3, or equivalently you can say that stress no, the relaxation constants are tau 1, tau 2, tau 3 and so on. So now in this case, now if you look at the total stress under constant strain, under constant strain epsilon naught, we will have total stress sigma t will be equal to stress now in this elastic element, in this Maxwell element, stress in this Maxwell element, sum of all those. So is stress in the elastic element would be E infinity into epsilon naught, and then stress in each Maxwell element would be equal to I going from, let's say, n number of Maxwell elements are there. So we will have sigma m naught I e to the power minus t upon, now for radiation constant or relaxation constant for each Maxwell element is going to be different. So let us say that is tau I. So now if we divide this by Young's strain epsilon naught, so sigma t upon epsilon naught is, let us say, the equivalent Young's modulus E, which is a function of time, will be equal to this side E infinity plus sigma m naught I upon epsilon naught is EI. So this will be equal to I going from 1 to n, and this is EI e to the power minus t upon tau I. So see, this is known as the Prony series. So that means equivalent Young's modulus is represented as a function of time with multiple Maxwell elements of what I have just drawn over here. So this one is known as the basically your Prony series, and you can, depending on the accuracy level you are looking for, you can choose the value of n. Minimum value
Sir,
of n, of course, 1, and maximum you can choose any number of terms depending on the accuracy requirement.
hello.
Yes. Yeah.
Sir, like I have one doubt regarding, like, are we modeling the complete rigid body, like rigid elastic body, by this model, this one single element?
Yeah, yeah. Say, let us say now we have a uniaxial sample. So that sample we are representing by so many elastic and viscous elements. That is what we are saying, that it is a, let's say, a cylindrical specimen of certain diameter. So that is represented by a number of this elastic and viscous elements. So
Okay.
this is a
So,
mathematical representation of that behavior.
sir, so like, will that element will be made up of multiple these currently which you have written Prony series? So
Yeah.
will we have multiple of Prony series to represent the whole shape, or will it be like only this
No,
one
one
Prony?
Prony series, one Prony series, one Prony series. That is what we are.
Okay, sir.
Yeah. So I think this is where I want to stop. I know I will continue further on this. So if now you have any other questions and doubts, you can ask. Anybody? Any
Sir,
doubt, question?
sir,
Yeah.
but then in that case, sir, are we neglecting the spatial variation of like epsilon and sigma?
No, they
Because
could be, this is at a, we are writing at a point. So there can be spatial variations. So although if the material is homogeneous material, so this Prony series constants would be same at no different locations, but the stress and strain can be different at different locations. So
okay,
I know in case of inhomogeneous material, even this E infinity, Ei and tau I, they would be function of spatial coordinate for inhomogeneous material.
okay, sir.
Yeah. So are there any other question? Okay, so if there are no further questions, I am stopping here. Thank you all for your attention.
Hello, sir.
Sir,
Sir, I
Yes.
had a doubt regarding the assignment.
Yeah.
Sir, so submission has to be made by all the 4 students, or one has to submit
I
and
think
name
I
all
have
the 4?
given there the group submissions are possible. So one person can make that submission, but you have to give the details in that. I have given group submissions possible in the grade score.
Sir, like for the coding part, like we have to contact Mr. Sumit, like
Yeah,
you
you can
mentioned.
contact. Yeah, if you have any doubts, you can contact Sumit. Yeah,
Sir, what's his full name, sir? Actually,
Sumit Kumar. He's a
Acha, Sumit
PhD
Kumar.
student. Yeah,
Okay, sir.
he's a PhD student.
Okay, sir.
Yeah. Okay, then I'm stopping. Thank you all for your attention.
Thank you, sir.